In the last video, we defined orthogonal sets, but in this video, we're going to take a little bit of a detour, and we're going to discuss what happens if we insist on the columns of a matrix to be orthogonal vectors. Specifically, we're working in some Rn or Rm, and the column vectors we want to say are orthogonal in that particular Rn or Rm. In fact, we're actually going to go a little bit further and insist that we have orthonormal columns, that they have unit length. We will call a matrix an orthogonal matrix if it's a square matrix, specifically a square matrix. We'll actually look at some matrices that are not square but still have orthogonal columns. But here, an orthogonal matrix itself is a square matrix where the column vectors form an orthonormal set in Rn. Now, do note that we are calling it orthogonal even though we are insisting on orthonormal columns. There's not really a separate concept of an orthonormal matrix. I don't know why they didn't call it an orthonormal matrix, but that's the names that they gave them, and I didn't name them, so sorry for any confusion about that. But an orthogonal matrix has orthonormal columns. So an example of an orthogonal matrix might be something like 1/3 times 1, 2, 2, 2, -2, 1, 2, 1, -2. Actually, that 2 looks like a 3. Why did you delete that one? I want to delete that one. There we go. So what are we actually dealing with here? Well, it doesn't look like that all of our columns are unit length, but we do have the 1/3 there. Technically, we're dealing with a 1/3, 2/3, 2/3, and so on. I just figured writing it out without the thirds in there might make it a little easier to see what the pattern is. But if we take any of these vectors and take its inner product with any of the other two, then we'll get 0. And if we take the magnitude of any of these vectors, we're going to get 1. Now, we could go ahead and do that. We could test every single one of them. We have to take how many inner products? Well, we have to take an inner product of each vector with all 3 of the other ones. That's 9 different inner products. Okay, but we can actually do it all at once. We have a theorem here, and this is sometimes actually taken as a definition of what an orthogonal matrix is. A square matrix, Q, is orthogonal if and only if the transpose times that matrix is equal to the identity matrix. So what are we basically doing if we're taking Q transpose Q? Well, let's first imagine that Q is the matrix with columns Q1 through Qn. If we take Q transpose Q, what are we actually doing? Well, first, when we transpose this, all the Q's turn into the rows. I'm going to leave out the 2's. Let's just do 1 through n. So we have all of our rows come from the original columns of Q. And then we have the columns of Q. And if we multiply this out, what is our first entry? Well, keep in mind this is in a sense, what we have here is an n by n times an n by n, but the first thing that we're going to have up here is this first row, the Q1 transpose, times this first column, this Q1. So that's what we have there. Then for this next one, we're still going to use the first row, but now we're going to use the second column. So we have Q1 transpose Q2, and so on and so forth, until we get to Q1 transpose Qn, Then we have here, well, now we're dealing with the second row, but now we're dealing with each of the columns. So Q2 transpose Q1, then Q2 transpose Q2, through Q2 transpose Qn, and so on and so forth. So down here we have Qn transpose Q1, Q2 it should be Qn transpose Q2 through Qn transpose Qn. So essentially what we have here is that the product Q transpose Q is literally just the matrix consisting of all the inner products of all the columns of Q. In fact, we could use that idea for any matrix. It's just very useful here because we already know something about these inner products. We said that the columns of Q are supposed to be orthonormal. That means that if we're ever dealing with with an I and j that are different, we automatically get 0. That means this Q1 transpose Q2 is automatically 0. We get a 0 here. We get a 0 over here. We get a 0 here. It's kind of filling in the ones that we have in our previous one. On the other hand, if the I and j are the same, if we have Q1 transpose Q1, that's equal to 1 because we have a unit vector. So a 1 here, a 1 here, a 1 here. So we end up with a matrix where all the diagonal elements are 1s and everything off of the diagonal is 0. Well, that is the identity matrix. And in fact, we can go the other way. The fact that we got the identity matrix here just means that this matrix of all the inner products, all the scalar products really, is equal to the identity matrix. So each of these has to be exactly what we want it to be for the columns of Q to be orthonormal. So if we wanted to show that this is actually an orthogonal matrix, we could go ahead and just take this matrix and multiply it by its transpose. In fact, let's go ahead and do that. And what am I going to do here? Well, I'm actually going to use the one where we've taken the 1/3 out. We can actually take the transpose of this matrix as it is and then multiply it together. So what is the transpose of that matrix? Well, we just take this matrix. We still have the 1/3. That doesn't really change. But then we just go ahead and swap everything. And kind of seeing that maybe I should have picked a different one where the transpose is not itself, but that's okay. The fact that its transpose is itself is kind of interesting, but a little bit off topic. We're going to multiply these two vectors together. We have, well, the 1/3 can come out in front. We have a 1/9. We have this row times that column. We have, so 1 times, 1 plus 4 plus 4. That gives us a 9. Then we have 2 minus 4 plus 2. Well, 4 minus... we have 2 plus 2 minus 4, so those all cancel each other out. We can do the same thing with all the other ones. We'll get a 0 here, we'll get a 0 here, we'll get a 9 here, 0, 0, 0, and 9. And I'll leave it to you to actually show that all the other ones do work out the way I claim. Now, of course, it doesn't look like we had the identity matrix, except we have the 1/9. So when we bring the 1/9 in, it changes all those 9s into 1s. And we have the identity matrix. That's what we wanted. Now, since we do know that the columns of an orthogonal matrix are, well, they're orthonormal, that means that they have to also be linear independent. If we have a square matrix that has linear independent columns, it's invertible. So that means that any orthogonal matrix is invertible. And because we know that Q transpose Q equals the identity, this actually means that Q transpose is the inverse of Q. So for any orthogonal matrix, or we can even take this as a definition, an orthogonal matrix is a square matrix whose inverse is the same as its transpose. It just happened in the example we just did, its transpose was itself, so it's kind of its inverse was itself. Kind of an interesting situation there. But the point here is that inverse being the transpose is equivalent to having the columns be orthonormal. This also means that orthogonal matrices lead to very nice linear transformations. If we say have L of x equal to Q times x, so here x's are in by one column vector, and we get an in by one column vector out of this. Let's see what happens if we take the inner product of any of L of x and L of y for any vectors x and y. Now, we're taking the inner product, we're working in Rn, so really we're working with a scalar product. So we can immediately turn this into the first one transpose times the second one. But of course, we're saying that this is given by Q, so let's go ahead and stick Q in there. So if Qx transpose and then Qy, we have the transpose of a matrix product. We know that we can take those matrices, swamp the order, and just put the transpose on those. But now we have Q transpose Q. Q transpose Q is the identity. We saw that just a minute ago. So this is really just X transpose Y, which is just the inner product of X and Y. So an orthogonal matrix is one where if you treat it as a linear transformation, or linear operator really, it doesn't change the scalar products of any of the inputs. We can also see that it doesn't change our magnitude. Remember the norm of L of x is really just the inner product of L of x with itself. And we just saw that, well, we can take the L's out without changing anything. So we just get the inner product of x with itself, which is just the norm of x squared. So this L doesn't change magnitudes either. These properties are summarized in this table. And they didn't use the notation L of x, they're just putting the Q in front of the x. But these are all characteristic of how orthogonal matrices behave. And they also use the 2 for the magnitude. But all this is the standard scalar product and magnitude in Rn. Now let's actually look at an example from the book. Specifically, we're going to look at example 6. We're going to look at the matrix Q, where Q is given as cosine of theta, negative sine theta, sine theta, and cosine of theta. So 2 by 2 matrix. Let's multiply this by its transpose. So we're taking that matrix. So I just copy that matrix down. But we're going to multiply it on this side by its transpose. So we'll still have the cosine and cosine in the same spots, but now we'll have the positive sign up here and the negative sign down here. If we multiply those two together, what do we get? And I'm going to write it out, but I'm going to abbreviate cosine by C and sine by S, just so my matrix isn't terribly huge. But what do we have in this first slot? We have cosine times cosine plus sine times sine. So C squared plus S squared In the next slot, we still are working with the same first row with the second column, so cosine times negative sine. So we have a negative CS. Then we have plus sine times cosine. In this slot here, we take the second row, but the first column, so negative sine times cosine, plus cosine times sine. And then finally, we have the second row and the second column. So negative sine times negative sine, so positive sine squared, plus cosine times cosine is cosine squared. And so here, well, obviously, here we're just taking something with it and adding it to its negative, so it's 0. Same thing here. And then we're using the fact that sine squared plus cosine squared is equal to 1. So we just get 1 in those two slots and 0 in those two slots. We have the identity matrix. So this matrix here, this Q, is an orthogonal matrix. Now, recall what this matrix actually does geometrically. We've talked about this back when we talked about what linear transformations do back in Chapter 4. This matrix here represents a rotation of the plane around the origin. Specifically, it rotates everything by an angle of theta in the counterclockwise direction. And what is this actually saying? Well, because we have these properties of orthogonal matrices, what this is really saying is that this matrix, this rotation, does not change any lengths or angles of anything that we actually are working with. If we had, say, a triangle over here, and we rotate it around, we're going to have essentially the same triangle. It's going to have the same angles and the same side lengths, but it's just going to be in a different location and a different orientation. But it might as well just be the same triangle. In fact, usually in geometry, we'd say they're congruent triangles. They're not exactly the same one because they're in a different place, but they might as well be. Now let's look at a matrix that has orthogonal, or really orthonormal columns, but is not necessarily square. So we're saying that we have A here with orthonormal columns, but we want to look at the least squares problem, which will mean that we'll have more rows than we have columns. If this was actually an orthogonal matrix, if this was a square matrix, then the least squares problem is really simple. The inverse is its transpose, and we get an exact answer. But here we're working with the least squares problem. And it's saying that if we have our column vectors are orthonormal, then we still have this same relationship that A transpose times A is the identity matrix. Because remember, that product is literally just the matrix of all the inner products of all the columns with themselves. And we're going to get the identity matrix. It's just that we're not multiplying together a square matrix. We're not using square matrices here, so we can't talk about them being invertible. And we don't get the other direction either. A times A transpose is not going to be the identity. But this does simplify things. Remember that the solution to our least squares problem, as long as we have a full rank matrix, and this is going to be full rank because the columns are linear independent because they're orthogonal to each other, then that is A transpose A inverse times A transpose B. This is our least squares solution to AX equals B. But if A transpose A is the identity, then we might as well not even have it here. The identity inverse is the identity matrix. So this all can just go away, and we're left with A transpose times B. So really simplifies that least squares problem. We can just multiply by the transpose of our matrix A, and we're done. We don't have to do anything more. Now, what if we actually don't have orthogonal columns? Well, we can actually use some of these ideas to simplify it a little bit as well. especially for some of the bigger matrices out there. But it's going to take a little bit more work, and we won't be able to finish that idea until we go through 5.6. So this is something that we're going to be working on throughout the next section as well. But we want to get started on it. We're going to generalize the idea of the projection. So remember, the least squares problem was really boiled down to projecting a vector onto a subspace, onto the span of a bunch of other vectors. Here we're going to say that we have a subspace S of our vector space V. We're going to take some other vector in V, and then we're going to use an orthonormal basis for S to find the projection really easily. So what we basically do is we take the inner product of X with all the basis vectors u1 through un, and we're going to use those as coefficients of a vector in S. Just take the linear combination of those u's with those coefficients that come from this inner product. We're going to call that P, and that P is going to be the projection that we're looking for. In fact, we can show that P minus X is in the orthogonal complement that is perpendicular to S. And we can also show that this vector P is the closest vector in S to X. Now, again, these are relatively easy proofs once you actually boil them down, and the book goes through them. I'm not really going to do that here, just in the interest of time. Just be aware that what we do in the first one is do that kind of expansion that we did in the proofs that we showed in the first video. And in the second one, we rely on the Pythagorean law. Just being able to expand out a norm of a sum into a sum of norms. Squares. As long as squares of norms turn into the sum of squares of norms. As long as we have orthogonality. But we're not going to get into that now, just because we don't really have time for it. And those theorems actually do work for any general vector space. But if we do know that we are working with Rm, then we can actually write it down even in a different form. We can turn that orthonormal basis for our subspace into a matrix, just make them the columns of our matrix, and then we can find that projection by just multiplying u by u transpose times the vector we're trying to project. So we're trying to project B into S, and we multiply that by that matrix. So here's actually where the other direction comes in. Remember, because U has orthonormal rows, this product, U transpose U, is the identity matrix. U times U transpose is not the identity, but it does have a use. It is the projection matrix. So we can call this capital P. It's the projection matrix onto the span I shouldn't say the span of, onto the column space of U, because that's what the span of the columns of U is. So this does have a definite use. It has a pretty easy thing to say here. You just multiply by this matrix, and we get the projection onto the column space. And so we're going to call we've been calling this the projection matrix. So let's kind of just move on. I want to actually solve a problem doing this, even before we get into the examples video. So this is actually from an example from the book. This is example 8. And what we're doing here is we're going to approximate the function e to the x by a line. Now, we have to be very specific here on the interval 0 to 1. We have to work with a particular vector space that we can actually put an inner product on. So we're going to be working in C of 0, 1. We're going to use the inner product, where the inner product of f and g is the integral from 0 to 1 of the product of f and g. And then we can actually we can solve the problem now. Until we have that inner product, it doesn't really work out too well. But what are we actually going to do? We want to approximate e of x by a line. So really what we're doing is looking at all the lines out there. So mx plus b type lines. And we want to project onto that subspace of C of 0, 1. Now, what we're doing here, we have the collection of all lines out there as a subspace, but it's spanned by vectors, 1 and x. And we could take 1 and x as a basis for the subspace of all lines. Unfortunately, it's not an orthonormal basis. We do have that the norm of 1, if we write this out, we have the integral from 0 to 1 of 1 times 1, and that just turns out to be 1. 1 is a unit vector. But x is not a unit vector, and it's not orthogonal to 1. So let's focus first on getting an orthonormal basis. And in fact, we'll focus first on the orthogonality, and then later on we can always scale it to make it a unit. Just divide by its magnitude. So let's try to find a vector that is orthogonal to 1. Actually, if I'm assuming here that I can rescale it later, let's assume that m is equal to 1, and that will simplify some of the work. So once I find an x plus b that's orthogonal to 1, I'm going to divide it by its magnitude. Now we have just using our formula, we have the integral from 0 to 1 of 1 times x plus b. We can do that one pretty easily. Well, I don't need the integral sign anymore. This should be 1/2 x squared plus b times x from 0 to 1. If we go ahead and plug in 1, we have 1/2 plus b, then plus 0. And so if these are supposed to be orthogonal to each other, this has to equal 0. That means that b has to be negative 1/2. So x minus 1/2 is actually orthogonal to 1. It's not a unit vector, though. What is its magnitude? Or magnitude squared. So magnitude squared is the inner product of it with itself, which just basically means that we're taking the integral of x minus 1/2 squared. Now this one is a little bit more involved because we have to expand this out. We have x squared minus x plus 1/4. We take that integral, we have a 1/3 x cubed minus a 1/2 x squared plus a 1/4 x. And then when we plug 0 in, everything goes away. So really, we just need to plug in 1. We have a 1/3 minus 1/2 plus 1/4, and that all simplifies to a 1/12. Remember, though, that this is the square of the magnitude, so we actually do need to take the square root of that. And so what do we have? We have that the magnitude of this is 1 over, now there is a 4 in 12, so I'm going to pull that out. The square root of 4 is 2, and then we're left with the 3 That's the other part of 12. So we have an orthonormal basis where u1 of x is 1, and u2 of x is the vector x minus 1 half, but then divided by 1 over 2 square root 3, or really we take 2 square root 3 times x minus 1 half. That's our orthonormal basis. Now we want to use that to actually project e to the x into this subspace. Now how do we do that? Well, we just need to take the inner product of e to the x with each of our unit vectors, or with each of our basis vectors. So what it is, and this is going to be c1. C1 is the inner product of e to the x with u1. We have the integral from 0 to 1 of e to the x times 1. That's actually not too bad. It's just e to the x from 0 to 1. When we plug 1 in there, we get e. When we plug 0 in there, we don't get 0. We get 1. So c1 is e minus 1. c2, well, this is a little bit more interesting. I'm just going to write out u2 here. But remember, we're taking the product of we're taking the integral from 0 to 1 of e to the x times u2. u2 has a 2 square root 3 and an x minus 1 half, or sorry, x minus 1 half, right? This one is a much more interesting integral. The way I went about doing it is integration by parts. I'm going to spare you the details just in the interest of time. But what do we get here? We get 2 square root 3 times e to the x times x minus 3 halves from 0 to 1. When we plug in those numbers, we end up with 3 minus e. Or wait, the 2 goes away. Technically, we have all these halves in there, so it cancels out that 2. We just have the square root of 3 times 3 minus e. So try that out if you want to. I'm not going to go through all these details. It's just pretty straightforward integration by parts. But the point here is that our projection vector, our projection function, is c1 times u1 of x plus c2 times u2 of x. Remember, u1 is just 1, so we have here e minus 1 as our first part. But then we're going to add that to c2, the square root of 3 times 3 minus e, times u2. And u2, remember, is 2 square root 3 times x minus 1 half. We can do a little bit of rearranging here. In fact, these square roots of 3 combine to get rid of any square roots. And we'll see that everything that's multiplied to the x, in fact, this 3 minus e times 2 times the 3 that we're going to get there, is a 6 times 3 minus e, x. And then the other stuff combines into a 4e minus 10. So our m is 6 times 3 minus e. Our b is 4e minus 10. And if we plot this line, then we'll get a line that's very close to e to the x. So here is e to the x and this line that we talked about, that we derived. Now, obviously, a lot of this doesn't look like it's anywhere close to approximating the line. But remember, our approximation was specifically for the interval from 0 to 1. So probably need to, here we go. Let's just do that. So from 0 to 1, we're looking from here to about here. And on that interval, those are not too far off. Now, they get a little further off at the endpoints, but at least in the middle, it seems to be as close as we possibly can get. If we made the endpoints a little closer, then in the middle here, it'd actually be further away. So it is as close as we can get overall on the interval. If we use a different interval, we'd have to actually get a different result. But that's just the way the least squares problem works. Now there is another way of approximating functions by easier functions that is very famous, and the book talks about it, but we don't really have time to go through it here, and we can't really give it the time that it really is due anyways. This is an idea of approximating functions by powers of sine, or well, not powers, by sine of mx and cosine of nx. So all the vectors that we talked about at the beginning of the first video and in the examples video from last section, there's a reason why we talked about those. People like to use those to approximate functions. It's an idea called, let me write it out here because the pronunciation won't really stand out to you necessarily. It's called Fourier Analysis. Unless you know French, that might not make any sense why that's pronounced Fourier. Fourier analysis is used frequently in physics and engineering, and obviously mathematics, but we don't really have the time to really get into it here. I do encourage you to at least read through what the book says about it, and if you actually expect to be in physics or engineering, you might want to look further into it, or you'll probably see it in other classes later on. But it is really just kind of the same idea. We're really just using those sines and cosines, and we are solving a least squares problem. It really just boils down to that. Alright, and that video got a little bit longer than I wanted it to. I'm going to leave it there. I am going to work some problems in the next video, but that's all the theory for now. See you there.